Well, this is it. This is the 12th video on the reactions of organic compounds. And to kind of pull away from the paper or the center and look to the sides here, I just want to, as we close, I'm going to try to keep it together here. We've had on the left some notes on structure, because it's so important to see beyond lines and letters, to see the shapes behind, for example, methane, CH4, or we have here butadiene, to see shapes, to see three-dimensional structures was so important. But to start all that, we had to really first come back to, we had to start with hybridization, understanding bonding of atoms through an orbital theory. It's just interesting as we close our last video of reactions of organic molecules for Organic Chemistry 1 courses. It's interesting, we considered at the beginning orbital overlap, S's and P's around carbon getting together to have new orbitals, sp3 hybrid orbitals. And it's just interesting that we're ending with Diels-Alder reactions where we're also considering overlap of orbitals. Not within the atom, but between two molecules. The HOMO, or highest occupied molecular orbital, pi, MO, of the diene, this is an occupied, so highest occupied, with lowest unoccupied orbital of the dienophile, the dp. This is our dp, dienophile, this is our diene. And in somewhat of a way we can draw an arrow saying this is rich to poor. Rich to, I'm going to hesitate to draw arrows because we really have to understand Diels-Alder reactions in terms of orbital overlap between the diene and the dp. So it's not as if we can just say negative goes and attacks a positive. The principle is still there where we have rich to poor, but we don't have a particular atom here that has a positive charge, and we don't have a particular atom here that has a partial negative charge. Much like you might have had, just to kind of use this box, this is not the same situation, where we had something like a hydroxide attacking a carbon connected to a halogen. That's not what we have here. Partial positive atom being attacked by a negative atom in this hydroxide. That's a very good way to quickly assess where, like let's go to the right here of our paper, reactions, SN2 reactions between a nucleophile and an RX. That's a very good thing, just to put the negative on the positive. That was a good place to start. And if we had, looking to the right again on just the border, if we had a proton, looking at how the pi electrons could reach out and having excess electron density that's accessible, pi electrons are accessible, and they're weaker bonds, we could just draw an arrow to that proton. And we could do this with an alkene, alkyne, and even a diene. We could attack protons in that way. But this really doesn't work, just finding the negative and finding the positive atoms and connecting them together just doesn't work with Diels-Alder reactions. So we have to go big. We have to look at atoms, plural, in the diene interacting with atoms, plural, in the dienophile. It's kind of weird. So let's go to some practical stuff first, maybe take a breather, then come back to orbital understanding of the Diels-Alder reaction. Well, first of all, you need to just recognize in a Diels-Alder reaction, and this is just going to be a video on the typical Diels-Alder reactions, where we do consider the diene attacking the dienophile, but we can actually show in molecular orbital theory that, I don't want to just, you can plug your ears if you want, that the dienophile, the diene gives to the dienophile some electron density, while at the same time the dienophile, the dp, the alkene, is giving electron density to the diene. So we typically in textbooks show just one of those two. So I'm going to do that. Also, I'm going to show the diene in a sense, bringing it to the dienophile. Let's go ahead and go through some practical matters. And you're saying, yeah, it's about time. I'm lost already. So what you do with the Diels-Alder reaction is you have to find the diene. You have to find those carbons in the diene at the 1,4 position. And you have to know that in the end they're going to connect to the 1,2 position of the dienophile. Now typically an alkene, sometimes an alkyne, it helps to have electron withdrawing groups off of the dienophile, like nitro groups, carbonyls hanging off of the double bond. That helps. But practically what we can do is say I'll find the 1,2 of the dienophile, the DP, and I have my diene shown here. And what I'm going to do is just do an electron pushing trick. It's not showing the mechanism. It's just showing how to practically get from reagents to products. So I can have pi to sigma transition, pi to pi transition, and pi to sigma. So just electron pushing here. Getting a cyclic transition state, because these are paracyclic cycloaddition reactions, meaning they happen through an intermediate that's cyclic, that's not even an intermediate, a transition state that's paracyclic. And in the end, we do add a ring, cycloaddition. No ring in the reagents to a ring. So we can draw this bond forming down here. This bond is going to be forming here. So we have a transition state, and it really should have a dot here also, saying that we're going to be making a bond here. But either way, you jump from the diene and dienophile in one step through a transition state. So it's just a one step. This is just a transition state, no valley up there, to the product. One step. And we have our new bond here, sigma bond. We have our new bond here. We lost the pi bond because it's using those 2 electrons, and the new pi bond is right here. Now this is a good thing to remember, that the new pi bond is still in relationship to the diene, is between the 1 and 4 position of the diene. So if you ever have to go backwards in this process, find the leftover double bond in the new ring. That is the 2,3 position of the diene, and you can walk it back. You can go backwards if you wanted to go back to the Diels-Alder reagents. So that's some practical stuff, connecting the 1,4 to the 1,2. Now this is giving us down below a hint of how it happens. These two don't come at each other straight on. Now I'm going to use 2 different dienes. This is a cyclic diene, where the carbons here, 1 and 4, are bridged, and our dienophile has 2 electron withdrawing groups. So we're going to treat these right here, where my fingers are, as electron withdrawing groups off of the alkene. So the way it works is these don't come at each other straight in the same plane. We come either just below or just above. So you can actually consider both at the same time. So we're always going to draw, it's just typical in most books, to draw the diene above, on top. So we're saying they have to kind of come in so that we can have the pi electron density interacting. And again, we're going to consider the diene to kind of be giving it to the dienophile. So giving electron density occupied in the diene and unoccupied in the dienophile. So let's look at that in the next page. And we're going to start going to orbital theory, so hang on. Here we go. Not too bad, I hope, if you watch the other video. What I have drawn here is the highest occupied molecular orbital of the diene, pi MO of the diene. So the 2 electrons that we are not going to talk about would be for the diene, 1, 2, 3, 4 carbons, and again, it doesn't matter, this is not influencing the pi bonding because it's sp3, it's just a bridged diene, would have gray, 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 no breaks. Well, that'd be the, I guess, lowest occupied MO, LOMO. But we are dealing with, because we have a diene, 2 electrons in each pi bond, so a total of 4, 2, 4, we're dealing with the next orbital up. So not all overlapping constructively, but having a node. That's what we're looking at kind of from the side. So we're kind of treating this as if we're looking at it from the side, and we're imagining that down here, like to your front, we have gray side of the pi bonding, and over here, up top, we have the gray. So they are opposite on either end, gray to white on the bottom. Now what we're going to do is bring in, and I'm going to treat these oxygens as those are carbonyls. These are CO bonds. So if we were looking at it just from the side, it would look something like this. And I apologize, just kind of giving it some sort of space. We're going to take that as represented by these two gray bonds here. These two here. These are my two CO double bonds, and they're withdrawing. They like to withdraw a lot of electron density from the alkene, and we want that because what we want to attack is the lowest unoccupied molecular orbital of the alkene. So here's our alkene. We know we have a pi bond, but we're going to pull some of that pi electron density out towards my fingers, towards the carbonyls, so that we can attack the lowest unoccupied, the antibonding MO, pi MO of the alkene. What's empty? We said it's there. You have to consider with every pi bond, if there's constructive overlap, there's destructive. So we're going to fill it up. The HOMO is going to fill up the LUMO. And the way we're going to do this, as it's shown here, is we're going to have this one come in a little bit on top. The alkene's coming a little bit on top. Now, here's something else I want to mention. Those carbonyls, where my fingers are going to come over into the mouth of the diene. This being our diene. They're going to come over the top. Why? Because there's some pi-pi interactions between the carbonyls, electron withdrawing groups, and the diene. So it tends to be favored. But as we bond, now I'm going to take my time on this. As we bond, these two groups that my fingers are on the alkene, will bend away from the bridge of the diene. They'll bend away. Let me just show that. So I'm going to go ahead and build it in front of you, and we'll be done here in about 2 minutes. So I'm going to build it as we start forming the bond. There's the 4 position and the 2 position. We're going to put the pi bond between the 2 and the 3 of the diene, that new pi bond. And we're going to have the 1 of the diene with the 1 of the dienophile. And as you look at it now, we can say that the bridge that's left in the diene that we used here, the bridge, this one doesn't have one, is farthest away from those electron withdrawing groups. You're going to see this very structure on the next slide. This very structure. I'm going to put it onto the side here. And just again say that if we have electron withdrawing groups, they tend to go over the top of the diene, and if there was a bridge, it bends down, and this would bend up. Now if it came on the bottom, the bridge would bend up, and these groups would bend down. So that's just an important consideration. Endo, we'll look at that more on the next slide, an endo orientation of these groups. Endo means into the mouth of the diene, if you want to treat that diene as a mouth, like a Pac-Man. The diene, the mouth of the diene, these groups face it. And they bend up as the bridge, if there was one, would bend down. So we have some idea now, I hope, of why this reaction occurs. It's happening as the orbital overlap between the HOMO, this is white on white, and gray on gray, that's constructive. That's helping to pull this structure together to make a Diels-Alder product. So initial interaction involves the HOMO of the diene and the LUMO of the dienophile, and that's really just the start of it. We could consider other overlaps, the HOMO of the alkene and the LUMO of the diene, but we're just going to show just one of these. And it's seen that this is constructive interference. So if we have, again, the orientation where it's not same plane, but a little bit off of the same plane, a little parallel planes, we can get this constructive overlap. All right, let's get to that endo and exo stuff that we talked about. Remember how we said we had our structure with the bridge and the mouth of the diene. We're going to bring those electron withdrawing groups. Now this is a nitrile groups, CN groups. But they would also be electron withdrawing, and we're going to have those going into the mouth of the dyne. Now where do they bend? They bend away from the bridge. And we're going to go ahead and bring this, I guess, on top. We're going to have this on top. So this bends up, and the nitrile groups, as we start to make bonds between, again, let's not forget what's making a bond, the 1,4 of the diene and the 1,2 of the dienophile. The 4 will be connected to the 2, and the 1 will be connected to the 1, these bonds. And we have these groups as far away from the bridge of the dyne as possible. Not on the same side like these hydrogens, but on the opposite side. That's called an endo product, coming from the endo orientation of those groups to the dienophile. Exo would occur if we had just big groups that don't have interaction with the dyne. These would have some pi-pi interactions with the dyne. If they were just alkyl groups, they'd be in the exo orientation, that is, closest to that bridging carbon. This is favored when you have large non-electron withdrawing groups. So let's look back again. We had our product. We do have that bridge, so we can change its, but it doesn't matter. We can change our perspective on it. That bridge, CH2 group, is here, and the electron withdrawing groups that were underneath as this thing formed are bent away. So this goes up, and these go down, and that's as far away as they can be in this Diels-Alder reaction. Now, Diels-Alder reactions are hard. You may want to practice them. Just one last thing, you can also go backwards with Diels-Alder reaction. Remember we said, if you're wanting to go backwards, find that find the new double bond formed. You can say, well, I know these had to be the 1,4 positions then, because I always see it between the 2,3 carbons of the dyne. And we could go backwards now. The 1,4, and we could break. And you say, well, how do you know these are trans? Well, because they're shown wedge and dash, so they have to be a trans orientation to each other in the DP. This is the dyne. So find your double bond and work backwards from there. So with this one, this is our 2,3. I guess we could have gone to the left here, but we're going to talk about this ring. This would be our 1,4 of the dyne, and this is the 1,2 of the DP. So we're going to go backwards and say, oh, this would be my diene, and this would be my dienophile. That's it. Hope you do a few Diels-Alder reactions before you take on some sort of assessment. Bye-bye.